This video is for visually impaired students and the chapter is metal ligand bonding in transition metal complexes. Transition metals have very good tendency to form coordination compounds or complexes. Though many attempts were made by different workers to explain the bonding and structure of coordination compounds, the main credit goes to the brilliant work of Werner. In 1893, Werner proposed a theory which is commonly known as Werner's coordination theory. This was the first successful attempt to explain the bonding in coordination complexes. In recognition of his work in this field, Werner was awarded Nobel Prize in 1913. He explained the bonding in these complexes on the basis of two types of valencies of the metal, with the primary valency corresponding to oxidation state and the secondary valency corresponding to coordination number. The secondary valency or coordination number determined the stereochemistry of the complexes. However, the Werner's assumptions were not based on theoretical justification, and the scientists started making attempts to find bases of bonding in these complexes. The first attempt in this regard was made by Sidgwick, who extended the Lewis theory of electron pair bond formation to explain the bonding in transition metal complexes. He suggested that metal ion or atom accepts electron pairs from ligands until it achieves the next noble gas configuration and gave atom effective atomic number. EAN is the total number of electrons possessed by the central atom ion and the electrons gained by it from ligands. However, this theory lacked fundamental basis and simply gave emphasis on the stability of inert gas configuration in coordination compounds. With the advances in theories of chemical bonding, three modern theories of bonding in transition metal complexes have been developed. These are number 1 valence bond theory, number 2 crystal field theory, and number 3 molecular orbital theory. In the present text, we shall discuss mainly crystal field theory of bonding. The valence bond theory has already been discussed in previous classes. Valence bond theory. The valence bond theory was developed by Linus Pauling and assumes the bonding between the metal atom or ion and the ligand to be purely covalent. It presents a simple description of metal ligand bonding using hybrid orbitals of the metal and the electron pairs of the ligands. The basis of valence bond theory is that the appropriate vacant atomic orbitals sp and d of the metal atom hybridize to give a set of hybrid orbitals which are directed towards the ligands according to definite geometry of the complex. The bonding in metal complexes arises when a filled orbital of the ligand containing a pair of electrons overlap with the vacant hybrid orbitals on the metal atom or ion, forming a covalent sigma bond called coordinate bond. In addition to a sigma bond, there is also a possibility of pi bond provided suitable orbitals are available on the metal atom and the ligands. The total number of metal atomic orbitals which undergo hybridization is equal to the coordination number of the central atom or ion. For example, for coordination number 6 complexes 2d, 1s and 3p orbitals, that is a total of 6 orbitals of the metal atom, are involved in hybridization. The d orbitals involved in the hybridization may be either inner n-1 d orbitals or outer n d orbitals, giving inner orbitals or outer orbitals complexes. For example, in case of octahedral hybridization, the orbitals may be 1 ns, 3p and 2 nd, or 1 ns, 3 np and 2 n-1 d. Similarly, for coordination number 4 complexes, tetrahedral structure can be considered to arise from bonding with 4 sp3 hybrid orbitals found by the combination of 1 ns and 3 np atomic orbitals, or square planar structure arising from bonding with 4 dsp2 hybrid orbitals using n-1 d, ns and 2p atomic orbitals. Some common type of hybridization of atomic orbitals and their geometries are given in table 1. If the hybridization is sp, shape is linear, sp2, shape is trigonal planar, sp3, shape is tetrahedral. If dsp2, shape is square planar. If dsp3, shape is trigonal bipyramidal. If sp3d, then shape is square pyramidal. If D2sp3 or sp3d2, then the shape is octahedral. Limitations of valence bond theory. The valence bond theory successfully explained many stereochemical and magnetic properties of coordination compounds. However, it has many limitations. The main limitations of valence bond theory are: it provides only qualitative explanation for complexes. Number 2, it does not explain the color and electronic spectra of complexes. Number 3, this theory fails to explain why some metal complexes in a particular oxidation state are low spin complexes while other complexes of the same metal ion in the same oxidation state are high spin complexes. For example, in the complexes CONH3 positive and COF6 negative, the oxidation state of cobalt is +3, but the former is low spin complex and the latter is high spin complex. Number 4, it does not predict the relative stabilities of different complexes. We know that certain complexes are labile in which the displacement of ligand takes place rapidly, while some are inert in which ligand displacement by another ligand is very slow. Valence bond theory does not explain the kinetic inertness of complexes such as Cr3 and low spin CO3 octahedral complexes. It does not explain the variations of magnetic moment values with temperature. Number 6, it does not take into account of the splitting of d energy levels. Number 7, it does not predict the relative stabilities of different structures. Number 8, the valence bond theory does not predict whether the 4-coordinate complex will be square, planar or tetrahedral. This can be explained only on the basis of magnetic moment values of the complex. For example, the decision about the geometry of nickel 2 complexes depends upon the magnetic moment values. For example, nickel 2 ion has the electronic configuration 3d8. If the complex involves sp3 hybridization, it would have tetrahedral structure. For the formation of tetrahedral structure, the 3d orbitals remain unaffected and the complex is paramagnetic. On the other hand, if the complex involves tsp2 hybridization, it would have square planar structure. This is possible if the two unpaired d electrons are paired up, thereby making one of the 3d orbital empty. There is thus no unpaired electron and the complex would be diamagnetic. It also fails to give a satisfactory explanation for the formation of square planar tetraamine copper 2 ion CuNH3 positive. Number 9, the valence bond theory does not tell us why water and halide ions commonly form high spin complexes while cyanide ions form low spin complexes. To answer some of the above problems, let us discuss other theories. Crystal field theory. The crystal field theory was developed by H. Bethe and V. Black. This theory is based on entirely different assumptions than the valence bond theory VBT. As we have already learned, the valence bond theory considers the bonding between the metal ion and the ligands as purely covalent. On the other hand, the crystal field theory considers the bond between metal ion and the ligand as purely electrostatic. This theory is based on assumptions that the metal ion and the ligands act as point charges and the interactions between them are purely electrostatic. In case of negative ligands, anions such as Cl negative, Br negative, Cn negative, the interactions with metal ions are ion-ion interaction. If the ligands are neutral molecules such as NH3H2O, the interactions with the metal ion are ion dipole interactions. For example, in the case of complex ion COF6 negative, the interactions are between CO3 positive and F negative ions, whereas in CONH3 positive, the interactions are between negatively charged end of NH3 molecule and CO3 positive ion. The central idea of this theory is that the electrons of the metal ion in the environment of other ions or molecules, as for example within the lattice of a crystal, are affected by the non-spherical electric field established by the surrounding ions or molecules. The electric field was called the crystalline field, but now it is called as crystal field. This is responsible for the name crystal field theory. Basis of crystal field theory. The basic assumptions of crystal field theory are: number 1, all transition metal ion is surrounded by the ligands with lone pair of electrons. Number 2, all type of ligands are regarded as point charges. The ligands may be either ionic F negative, Cl negative, Cn negative, etc., or molecules such as H2O, NH3CO, etc. If the ligand is a neutral molecule, then the negative end of the dipole is oriented towards the metal ion. For example, ammonia NH3 is polar molecule having negative charge on N and positive charges on H atom. Similarly, water is also polar with charge on O and partial positive charge on H atom. Number 3. The interactions between the metal ion and the negative ends of the anion or ion dipoles is purely electrostatic. That is, the bond between the metal and ligands is considered 100% ionic. Number 4. The ligand surrounding the metal ion produce electric field, and this electric field influences the energies of the orbitals of central metal ion, particularly d orbitals. Number 5. In the case of free metal ion, all the 5 d orbitals have the same energy. These orbitals having the same energies are called degenerate orbitals. This means that an electron can occupy any one of these 5 d orbitals with equal ease. However, on the approach of the ligands, the orbital electrons will be repelled by the lone pair of the ligands. Their repulsion will raise the energy of the d orbitals. If all the ligands approaching the central metal ion are at equal distance from each of the d orbitals, the energy of each orbital will increase by the same amount. Therefore, these orbitals will still remain degenerate, but they will have higher energy than before. But we know that d orbitals have different orientations, and therefore these orbitals will experience different interactions from the ligands. The orbitals lying in the direction of the ligands will experience greater repulsion and their energies will be raised to greater extent. On the other hand, the orbitals lying away from the approach of the ligands will have lesser interactions and therefore their energies will be raised to lesser extent. Therefore, due to electric field of the ligands, the energy of the 5d orbitals will split up. The conversion of 5 degenerate d orbitals of the metal ion into different sets of orbitals having different energies in the presence of electrical field of the ligands is called crystal field splitting. This concept forms the basis of crystal field theory. Number 6. The number of ligands and the arrangement around the central atom ion will have same different effect on the relative energies of the 5d orbitals. In other words, the crystal field splitting will be different in different structures with different coordination numbers. Number 7. The magnetic properties, spectra and preference for particular geometry can be explained in terms of splitting of d orbitals in different crystal fields. Thus, to understand the crystal field theory, it is essential to have a clear picture of the disposition of the 5d orbitals in space and the geometrical arrangement of the ligands around the central metal ion. We have illustrated this concept by considering the complexes with coordination number 6 and 4, which are very common. Shapes of d orbitals. There are 5 d orbitals. These are generated as dxy, dyz, dzx, dx square minus y square and dz square. The shapes of these orbitals are described below. Number 1. The 3 orbitals dxy, dyz and dzx are similar and each consists of 4 lobes of high electron density lying in xy, yz, zx plane respectively. These lobes lie in between the principal axis. For example, in case of dxy orbitals, the 4 lobes lie in xy plane in between x and y axis. Number 2. The dx square minus y square orbitals has also 4 lobes of high electron density along the principal axis x and y. It may be noted that this orbital is exactly like dxy orbitals except that it is rotated through 45 degree around the z-axis. Number 3. The dz square orbital consists of 2 lobes along the z-axis with a ring of high electron density in the xy plane. It may be noted that although dz square and dx square minus y square orbital do not look to be similar, yet they are equivalent so far as interactions with the metal ions are concerned. The dz square orbitals can be regarded as a linear combination of 2 orbitals, dz square minus x square and dz square minus y square, each of which is equivalent to the dx square minus y square orbital as shown below. However, it may be noted that these 2 orbitals do not have independent existence, but the dz square orbital can be thought of as having the average properties of the two. Since both the orbitals dz square minus x square and dz square minus y square have high electron density along z-axis, therefore dz square orbitals has a large fraction of electron density concentrated along z-axis. Moreover, one of the component orbital dz square minus x square has lobes along the z-axis also, and the other has lobes along the y-axis. The resultant d orbital has electron density in xy plane shown as donut ring or a collar. Crystal field splitting in octahedral complexes. In an octahedral complex, the metal ion is at the center of the octahedron and the ligands are at the 6 corners as shown in figure. The 3 axes x, y, z point along the corners of the octahedron and are also shown. Let us suppose that the metal ion Mn positive has a single d electron. In the free ion, when there is no ligand, the electron can occupy any one of the 5d orbitals because all of them are of same energy and are called degenerate orbitals. However, in the orbitals complex mx6, all the d orbitals will not remain of equal energy. This may be easily understood by considering the shapes of these orbitals in the octahedral field of the ligands. The comparison of arrangement of d orbitals in figure 4 shows that the 2 lobes of dz square orbitals and 4 lobes of dx square minus y square orbitals point directly towards the corner of the octahedron where the negative charges of the ligands are concentrated. The remaining 3 orbitals are oriented in between the axes. In the case of octahedral complexes, the former 2 orbitals are designated as Eg orbitals, while the latter 3 orbitals are designated as T2G orbitals. As the 2 ligands approach the central ion along the axis, the Eg orbitals are repelled more than T2G. In other words, the energy of the dz square and dx square minus y square orbitals increase much more than the energy of the dxy, yz and dzx orbitals. It should be remembered that when a charge is repelled by a similar charge, its potential energy increases. The greater the repulsion, the greater is the increase in energy. Thus, in octahedral complexes, the 5d orbitals split up into 2 sets. One set consisting of 2 orbitals of higher energy, that is Eg orbital, and the other set consisting of 3 orbitals of lower energy, T2G orbital. The phenomena of crystal field splitting in an octahedral complex is illustrated in figure 5. The energy difference between 2 sets of d orbitals, T2G and Eg, is called crystal field splitting energy and is symbolically represented as delta naught. The subscript naught stands for octahedral. The magnitude of delta O varies for different complexes. The crystal field splitting is also measured in terms of another parameter called dq. The two are related as delta O is equals to 10 dq. These two parameters are very commonly used. It may be noted that crystal field splitting occurs in such a way that the average energy of the d orbitals does not change. This is known as barycenter rule, which is similar to the center of gravity type rule. This means that the decrease in energy of the set of orbitals that lie at the lower energy level must be balanced by the corresponding increase in other set. Therefore, in terms of total energy 10 dq, the energy of each of the 2 Eg orbitals is raised by 6 dq, and the energy of each of 3 T2G orbitals is lowered by 4 dq. In terms of delta naught, the energy of each of the 2 Eg orbitals is raised by 3 by 5 delta O, and the energy of each of the 3 T2G orbitals is lowered by 2 by 5 delta O. The value of 10 dq or delta O is measured spectroscopically. In figure 5, we observe that initially the energies of all the 5d orbitals are raised equally as shown in state 2. This would be observed if the field created by the ligands was spherically symmetrical. However, the energies of d orbitals split into 2 sets because of different orientation of the orbitals towards the ligands as shown in state 3. Crystal field stabilizing energy. We have learned that in an octahedral field, the energies of 5d orbitals split up. 3 orbitals are lowered in energy T2G and 2 orbitals are raised in energy Eg. We know that electrons always prefer to occupy an orbital of lower energy. For example, in the case of D7 system, the d electrons will prefer to occupy a T2G orbital and is therefore stabilized by an amount equal to 0.4 delta O or 4 dq. The amount of stabilization provided by splitting of the d orbitals into two levels is called crystal field stabilization energy. It is abbreviated as CFSE. Thus, in octahedral field, for each electron entering into the T2g orbital, the crystal field stabilization is minus 4 dq, and for each electron entering into the Eg orbital, the crystal field destabilization energy is plus 6 dq. Thus, the CFSE is calculated as the algebraic sum of minus 4 dq per electron in T2g level and plus 6 dq for each electron in Eg orbital. CFSE for various octahedral complexes. Number 1. For a D1 system, electrons will be present in any one of the three T2g orbitals. The electronic configuration may be written as T2g1. The crystal field stabilization energy is minus 4 dq. Number 2. For a D2 system, the electrons will occupy T2g orbitals with their spin parallel in accordance with Hund's rule. The electronic configuration is T2g2 and the crystal field stabilization energy is minus 8 dq. Number 3. Similarly, for a D3 system, the electronic configuration is T2g3 and the crystal field stabilization energy is minus 12 dq. For a D4 system, there are two possibilities. All four electrons may occupy T2g orbital with one electron gets paired. The electronic configuration may be written as T2g4. And B is the three electron occupy T2g orbitals and the fourth electron goes to one of the Eg orbital. The configuration may be written as T2g3 Eg1. The actual configuration may be decided on the basis of delta naught and the pairing energy P, that is the energy required to pair the electrons with one another. The configuration A is possible if delta O is greater than P. These complexes are called strong filled complexes because delta is large. In this complex has less number of unpaired electrons and is called low spin complex. The configuration B is possible if delta O is less than P. It is called weak field and the complexes are called weak field complexes. In that case, maximum number of electrons remain unpaired and the complex is called high spin complex. If delta O is greater than P, then this complexes are low spin. If delta O is less than P, then high spin complexes. As shown above, for a low spin complex having T2g4 configuration, CFSE is equals to 4 into minus 4 dq, that is minus 16 dq. However, if we take into account pairing energy also, the net CFSE is equals to minus 16 dq plus P. On the other hand, for a high spin complex having the configuration T2g3 and Eg1, CFSE is equals to 3 into minus 4 dq plus 1 into 6 dq is equals to minus 6 dq. Number 5. For a D5 system, there are two possibilities. All the 5 electrons may occupy T2g orbitals with two orbitals get paired. The electronic configuration may be written as T2g. This is possible if delta O is greater than P and the complex will be called strong field or low spin complex. Number B. The 3 electrons occupy T2g orbitals and the electrons occupy Eg orbitals. The electronic configuration may be written as T2g3 Eg2. This will be possible if delta O is less than P and the complex is called weak field or high spin complex. The CFSE in these two type of complexes will be for strong field when delta O is greater than P, CFSE is equals to minus 20 dq plus 2P. Weak field, if delta O is less than P, then CFSE is 0. Similarly, for D6 and D7 system have two possibilities depending upon relative magnitude of crystal field splitting energy and the pairing energy of the electrons P. For a D6 system, example CO3 positive ion, A strong field when delta O is greater than P, CFSE is minus 24 dq plus 2P, and for weak field CFSE is minus 4 dq. For D7 system, when there is strong field, CFSE is minus 18 dq plus P, and for the weak field it is minus 8 dq. The D8, D9 and D10 system have only one possible configuration. This is because if we assume the complex to be high spin, the first 5 electrons would go one each into the 5d orbitals and the remaining 3, 4, 5 electrons would fill T2g and Eg orbitals. But if we assume the complex to be low spin, the first 6 electrons would fill the T2g orbital and the remaining 2, 3, 4 electrons would go into the T2G orbital. In both cases, the configuration will be same. Therefore, there is only one possible configuration for D8, D9, D10 system. For a D8 system, for nickel 2 positive ion CFS is minus 12 dq, and for CO2 positive ion it is minus 6 dq. For a D10 system, for Zn2 positive ion CFS is 0. The d electron configuration for weak and strong field of octahedral symmetry are given in figure 6. The crystal field stabilization energies for metal ions having different configuration are summed up in table 2. It may be noted that for strong fields, the electrons always pair up in the lower level, first filling it before entering the higher energy level. For weak fields, each orbital, whether of high Eg or low T2G energy, receives one electron each before any pairing starts. Therefore, weak field configuration always have the same pairing scheme as the free ions. Crystal field splitting in tetrahedral complexes. The coordination number for tetrahedral complexes is 4. The tetrahedral arrangement of 4 ligands surrounding a metal ion may be visualized by placing ligands on the 4 of the 8 corners of the cube. The directions x, y, and z point to the center of the face of the cube. From figure 7, it is clear that the orbitals dx, y, y, z, zx point between x, y, and z axes, whereas the orbitals dx square minus y square and dz square point along x, y, z axis. It is clear that in tetrahedral field, none of the d orbitals point exactly towards the ligand, and therefore the splitting of energy will be less than that in octahedral field. The 3 d orbitals dx, y, dy, z, and dzx are pointing close to the direction which the ligands are approaching, while the 2 orbitals dx square minus y square and dz square are lying in between the ligands. Therefore, the energies of the 3 orbitals will be raised while the energies of the 2 orbitals will be lowered. Thus, in presence of tetrahedral field, the degeneracy of 5d orbitals split up as number 1. The 2 orbitals dx square minus y square and dz square become stable and their energies are lowered. These are designated as E orbitals. The 3 orbitals dx, y, y, z, and zx becomes unstable and their energies are raised. These are designated as T2 orbital. The magnitude of CFSC is the difference between E and T2 orbital and is designated as delta T. It is also measured in terms of dq, and delta T is equals to 10 dq. If we compare the magnitude of crystal field splitting in octahedral and tetrahedral complexes, it has been observed that the crystal field splitting in tetrahedral complexes is considerably less than in octahedral complexes. It has been found to be delta T is equals to 4 by 9 of delta naught. Reasons for smaller value of crystal field splitting in tetrahedral than in octahedral complexes. There are 2 reasons. Number 1, in tetrahedral complexes there are 4 ligands while there are 6 ligands in octahedral. Therefore, lesser ligands produce less CFSC. The crystal field splitting in tetrahedral field is about 2/3 of the octahedral field. Number 2, in tetrahedral field, none of the orbital is pointing directly towards the ligands and therefore splitting is less. Since the magnitude of CFSC in tetrahedral field is quite small and is always less than the pairing energy, therefore the pairing energy will never be energetically favorable. Thus, all the tetrahedral complexes are high spin complexes. No tetrahedral complex with low spin has been found to exist. CFSC for tetrahedral complexes. As we know that an electron always prefers to occupy an orbital of lower energy since average energy of d orbitals does not change. Therefore, in terms of 10 dq, the energy of each of the e orbital is lowered by 6 dq and the energy of each of the t2 orbital is raised by 4 dq. CFSC is therefore calculated as the algebraic sum of minus 6 dq per electron in e orbital and plus 4 dq for each electron in t2 orbital. In terms of delta t, the energy of each e orbital is lowered by 3 by 5 delta t, while each of the t2 orbital is raised by 2 by 5 delta t. For example, for D1 system, electronic configuration is E1, therefore CFSC is minus 6 dq. For D2 system, the electronic configuration is E2, therefore CFSC is minus 12 dq. For a D3 system, the electronic configuration is E2 T21. As already discussed, crystal field Splitting in tetrahedral field is quite small and is always less than the pairing energy. Therefore, pairing does not occur and most of the complexes are high spin complexes. Therefore, CFSE is minus 8 dq. The CFSE for complexes with metal ions having different configuration of d orbitals in tetrahedral field are given in table 3. Crystal field splitting in tetrahedral and square planar complexes. The splitting of d orbitals in tetragonal and square planar complexes can be easily understood from the non-splitting of d orbitals in octahedral complexes. This is because tetragonal and square planar geometries can be understood by withdrawing two trans ligands from an octahedral complex. This process is called elongation. Generally, we consider the removal of trans ligands along the z-axis. As the ligands lying on the z-axis are moved away, the ligands in the xy plane tend to approach the central ion more closely. As a result of increase in metal ligands bond along the z-axis, the repulsion from the ligands to electrons in dz square orbital decrease, and therefore the energy of dz square orbital is decreased relative to that in octahedral field. At the same time, the metal ligand bond along x and y are shortened so that the d orbital in xy plane dx square minus y square experiences greater repulsion from the ligands and therefore its energy is raised. Similarly, the dxz and dyz orbitals are lowered in energy because of decrease in repulsion effects along the z-axis while the energy of dxy orbitals is raised. The resulting splitting pattern is shown in figure 10. Thus, this state represents tetragonally distorted octahedral structure. As the trans ligands lying along z-axis are completely removed, a square planar complex is formed. In the square planar complex, there is further rise in the energies of dx square minus y square and dxy orbitals and a further fall in the energies of dz square, dxz and dyz orbital as shown. It has been observed that in square planar complex, the energies of dz square orbitals falls even below the dxy orbital. The change of an octahedral complex to tetragonally distorted octahedron and finally to square planar arrangement is shown in figure 11. It may be remembered that tetragonally distorted structure can also be obtained when two trans ligands are brought closer to the metal ion. This is called flattening of an octahedron. This is shown in figure 12, where figure 12a shows elongation of octahedron. In flattening of octahedron, the two terms ml bonds are shortened while other 4 ml bonds becomes large. The splitting of energies of d orbital will be reverse of what has been observed in the case of elongation. Crystal field splitting in trigonal bipyramidal complexes. The coordination numbers for trigonal bipyramidal complexes is 5. In trigonal bipyramidal geometry, the three ligands lie along the corners of an equatorial triangle at an angle of 120 degrees each, forming the pyramidal base in xy plane. The two ligands lie perpendicular to the base triangle along z-axis as shown in figure 13. It is clear from figure 13 that the dz square orbitals points exactly towards the ligands and therefore it will be most unstable and hence its energy will be raised to the maximum extent. The two orbitals, that is dx square minus y square and dxy, lie in xy plane. The lobes of these two orbitals do not point exactly towards the ligands but close to the direction in which the ligands are approaching and hence will be stable in comparison to dz square orbital and their energies will be lowered. Similarly, the other two orbitals, that is dyz, tzx, lie quite away from the approach of the ligands and hence will be lowered to greater extent than even dx square minus y square and dxy orbitals. The splitting of 5 t orbitals in trigonal bipyramidal field of ligands is shown. Factors determining the magnitude of crystal field splitting. The following factors influence the magnitude of crystal field splitting. Number 1. Nature of ligands. Spectrochemical series. The crystal field theory depends upon the nature of ligands. The greater the ease with which the ligands can approach the metal ion, the greater will be the crystal field splitting caused by it. The ligands which cause only a small degree of crystal field splitting are called weak filled by it. The ligands which cause only a large splitting are called strong filled ligands. The spectrochemical series is an experimentally determined series. It is very difficult to explain the order because it incorporates the effects of both sigma and pi bonding in general. The variation in the splitting is caused by a number of factors such as number A. Small ligands can cause greater crystal field splitting because they can approach the metal ion closely. For example, F negative ion produce more delta O value than large Cl negative and Br negative ions. B. The ligands containing easily polarizable electron pair will be drawn more closely to the metal ion. Number C. The ligands which have greater tendency to form multiple bonds such as Cn negative and NO2 negative cause greater crystal field splitting. The very high crystal field splitting produced by Cn negative ligands, about double that for weak ligands like halide ions. This is attributed to the pi bonding in metal. The metal donates electrons from a filled T2G orbitals into the vacant orbital on the ligand. The following pattern of increasing sigma donation is observed: halide donors, then O donors, then N donors, then C donors. The common ligands can be arranged in increasing order of crystal field splitting delta. The regular order is called spectrochemical series. The order remains almost same for different metal ions. The spectrochemical series in the increasing order of CFSC is given below: I negative, Br negative, SCN negative, Cl negative, NO3 negative, F negative, OH negative, OX2 negative, H2O, ADTA, PYNH3, EN, DIPY, orthophenol, NO2 negative, Cn negative. From the series, it is clear that CO, Cn negative, and NO2 negative are strong field ligands, whereas I negative, Br negative, and are weak ligand fields. In general, the ligands up to NH3 are called weak filled ligands, while those on right of NH3 are called strong filled ligands. The order of spectrochemical series remain practically same irrespective of the transition metal ions. Oxidation state of metal ion. The magnitude of the crystal field splitting depends upon the oxidation state of transition metal ion. The metal ion with higher oxidation state cause large crystal field splitting than is done by the ion with lower oxidation state. For example, the crystal field splitting energy delta O for COH2O6 positive complex in which the oxidation state of cobalt is +3 is 18,600 cm inverse, whereas for the complex COH2O6 positive in which the oxidation state of CO is +2, delta O is 9,300 cm inverse. Similarly, for the complex FeH2O6 positive and FeH2O6 positive in which iron has oxidation state +3 and +2 respectively, the values of delta O are 13,700 cm inverse and 10,400 cm inverse respectively. This is clear from the following data in which crystal field splitting energies for hexa aqua complex of M2 positive and M3 positive ions of the first transition series are given. Similarly, for complexes having other ligands, the delta O values in lower oxidation states are similar than delta O values in higher oxidation states, for example. Number 3. Types of d orbital transition series. The extent of crystal field splitting for similar complex of a metal in the same oxidation state increased by about 30 to 50% on going from 3D series to 4D series. The increase is almost of the same amount on going from 4D series to 5D series. This may be explained on the basis that 4D orbitals in comparison to 3D orbitals are bigger in size and extend farther into space. As a result, the 4D orbitals can interact more strongly with the ligands and therefore the crystal field splitting is more. Similarly, 5D orbitals are bigger than 4D orbitals and delta O for the third transition series is more than that for the second transition series. This is evident from the following data. Number 4. Geometry of the complex. As mentioned earlier, the crystal field splitting energy of tetrahedral complexes is nearly half the value of delta O for octahedral complexes. For example, In other words, the value of splitting energy for tetrahedral complex in general is small as compared to the pairing energy P. The tetrahedral complexes are therefore mostly high spin complexes. Thank you for watching.